This tutorial will provide an overview of some of the properties associated with the cable object. The cable object is a catenary element with two primary characteristics. 1. All external loads must be resolved into axial forces. The element has axial stiffness only and no bending stiffness. And 2. It is highly nonlinear. Forces in the object are dependent upon its shape. To illustrate these two traits, we have created two cable objects. Each cable spans a distance of 288 inches. The top cable has a sag of 2 inches and a total undeformed length of 288.02 inches, while the bottom cable has a sag of 12 inches and an undeformed length of 289.33 inches. Although there is a relatively small difference in the undeformed lengths, there is a significant difference in the axial forces in the cables. When subjected to self-weight, the cable in the top has an axial force of 1.47 kips, while the bottom cable has only 0.25 kips. In this case, the closer the cable is to horizontal, the larger the axial force must be to support the vertical weight. As just stated, cable shape has an enormous impact on cable forces, so it is important to accurately determine the drape. SAP 2000 offers a powerful tool for the determination of cable shape, a so-called shape finder, which we will now demonstrate. We start by selecting the cable, and then go to the Edit, Edit Lines, Edit Cable Geometry command to bring up the cable geometry form. The cable geometry is generated from the cable type. Our first choice is a shape that gives minimum tension. For a cable with an area of 1 square inch spanning 288 inches, this tension is 0.06 kips. The sag for this cable is 97.2 inches in the deformed state, which includes strain deformation, and virtually an identical sag in the undeformed state with no load. The program also tells us the lengths for both states and the relative lengths as compared to the chord length of 288 inches. The program uses this information to generate point coordinates for 17 locations along the cable. This defines the shape. This geometry defines a single object. Multiple objects are not being generated. As a general rule, a single cable object is adequate to model each cable unless you wish to add concentrated loads or discretize mass along the cable for dynamics. The number of cable segments may be altered here. The next option allows for a shape based on a minimum tension at the other end. You can also find a shape by specifying a tension at an end. We will input 0.1 kips. This changes the sag to 32.99 inches. We can do the same thing at the other end if desired. The next option allows us to generate the shape by specifying the amount of horizontal tension. Here we input 0.05 kips. This amount is the horizontal component and results in a sag of 62.14 inches. The maximum vertical sag option allows us to specify the vertical sag for the shape. With an inputted sag of 12 inches, The tension goes up to 0.25 kips. The next option allows for the specification of sag to be done from the lowest end point. We will input a sag of 12 inches below the lowest end. Now the tension at the two ends is different due to the fact that the ends are not at the same elevations. This is the 12-inch sag that we specified. The next shape generation option is to create a shape based on the undeformed length. If we specify an undeformed length of 288 inches, the sag in the deformed state drops to 1.47 inches. And the tension force goes up to 2 kips. The last option available to specify cable shape is to input the relative undeformed length. A ratio of 1 indicates that the undeformed cable has the same length as the cord. Here, we will increase the relative length very slightly to 1.001. But notice how significantly the tension force drops and the sag increases. This shows how critical determining the correct shape is to the accuracy of the overall model. To reiterate, the only purpose of this form is to find the starting shape of the cable as shown in the coordinates table. It does not set the cable forces. Now we will create a model using cable objects. It will be a guide tower 200 feet tall. The single mast tower is comprised of an 18-inch diameter pipe pinned at the base and guide with 3 cables at the midspan and 3 cables at the top. The guys will have an area of 0.34 inches square with an initial target tension of 8.5 kips. The tower will be subjected to dead load and a wind load of 120 pounds per linear foot. The analysis will be nonlinear, as models utilizing cables always require a nonlinear analysis. We start by defining a grid that is 100 feet wide by 200 feet tall. Switching to inch units, we will define the tower mast using the Define Section Properties Frame Sections command. We will add a new pipe property called Mast. The outside diameter will be set to 18 inches with a wall thickness of ½ an inch. Next, we will define a cable section. We will call it cable with an area of 0.34 inches square. Next, we will draw the mast. From bottom to top. And then add the pin support to the base. We will now add one set of cables in the XZ plane. We draw them so that the eye end is at the ground. This opens the cable geometry form, where we will select a cable type of tension at eye end. We will use our target tension of 8.5 kips to determine the shape. Repeat this step for the upper cable. This gives a deformed sag of approximately 10 inches, while the relative length for the undeformed case is less than 1. This signifies a taut cable. The starting geometry of the cables is now set. Next, we will apply the pinned restraint to the base of the cables. We will replicate the cables and support just drawn at 2 other locations in the model. We will do a radial replication about the z-axis, placing the cables 120 degrees apart. Now we define our load patterns. We will have a dead load pattern with self-weight, a target pattern for the application of the target forces in the cable, and a wind load pattern. We will not use the automated lateral load option, as we will apply the wind load directly. Next, we will set the starting force in the cables. Select all of the cable objects, and go to the Assign Cable Loads command. Here we will select the target force option, although we could also use strain or deformation to tension the cables. The load will be in the target pattern, and we will use a target force of 8.5 kips, applied with a relative location of 0, which is the ground. Next, we apply the wind load to the mast, using the Frame Loads command. The load goes in the wind pattern, and we will use pound-feet units. The load will be applied in the Y direction with a magnitude of minus 120 pounds per linear foot. The last thing we need to do prior to running the analysis is to define our load cases. The program has automatically created load cases. We will delete modal as we are not doing any dynamic analysis, and that leaves us with 3 cases based on our defined load patterns: dead, target, and wind. However, we need to modify these to obtain the correct model behavior. For the target case, a load case type of static is okay, but it must be nonlinear since cables are included. The formulation of the cable object includes nonlinear geometric effects, which means that we do not need to perform a large displacement analysis to get the correct behavior for the cables. However, you may wish to consider P delta for the other objects in your model, such as the mast in this example. In addition to our target cable tensions, we also want to include the self-weight dead loads in this analysis. A check of the nonlinear parameters shows that we can set the target force iterations as well as the convergent tolerance and the acceleration factor, but we will leave all of them set to their default values for this analysis. Next, we will modify the wind load case. Again, we will set it to be a nonlinear analysis type. However, in this case, rather than starting from 0 initial conditions, we will start from the end of the target nonlinear case. This will cause the cables and model to be in the correct state when the wind load is applied. We can now delete the dead load case, as these loads are included in the target case. We are now ready to run the analysis. Note that our two nonlinear static load cases are set to run. After the analysis, the axial force diagram for the target load case is displayed. A right-click on a cable brings up the force diagrams, and we see that the force in the cable is 8.478 kips versus a target of 8.5, which is very good. Right-clicking on some other cables shows similar good results. Next, we will display the axial forces due to the wind load case. For the first cable, which is perpendicular to the wind load, the axial force is 8.7 kips, not too different from the target. However, for the cable that is only 30 degrees off from the direction of the load, the tension shoots up to 14.6 kips, while the cable that is on the leeward side slacks off to only 2.7 kips. If we rotate the 3D view, we can see how the cables on the leeward side are less loaded, while those closer to windward carry more load. In summary, SAP 2000 provides an elegant tool for the modeling of cable structures, offering a powerful shape finder with many options for generating geometric coordinates, as well as an object that inherently incorporates geometric nonlinear effects. This concludes this tutorial on cable objects.